So hello guys, welcome to my lecture. This is Tyler. I'm here, also known as the Math Tipper. So following the Open Math project I've created, this is the first lecture of MATH001PB, which is single variable calculus proof based. So in high school, you may already have learned about single variable calculus before, but like most curriculum doesn't use a formal math approach to teach it and only do it as like an intuitive way. So in this course, I'll present the concepts in single variable calculus with a proof-based focus, like the propositions and theorems will be proved again. So it's not gonna be tell you like it's true and then you need to remember it's not that way. So in the first module, we'll go through the general definitions and properties of functions, including the definitions of functions, like composition of functions, injectivity, surjectivity, inverse functions, boundedness, monotonicity, and some more concepts. So before we go on the first subsection, let's first familiarize ourselves with the sets and logic notations first. Okay, so these are the set notations. So the first two notations is about whether an element is a member of the set. So in the first notation, this means that X is a member of the set A, and the second one is X is not a member of set A, just like the symbol is like equal but with the set in symbol. So second ones are the set builder notations. So you may either list out all of the set elements, like in the first one, set of ABC, so it's the set containing all the elements ABC, or you may set a restriction to the set by drawing a vertical line. And this notation means that the set of all X in A such that X is larger than 5, okay? So there's also a unique set that contains no element. It's called empty set, and it's like a zero with a stroke, okay? So this next one is the subset notation, which means A is a subset of B. So it means that every element of set A is also an element of set B, okay? So maybe I'll say that, for example, a set, the R is the all real numbers set, so it's B. So if you set the set to, for example, 1, then 1 is a subset of R, okay? So, and then the next one is A is a proper subset of B. So that means A is a subset of B, but A is not equal to B. So you may also say that for every element of A, set A is also an element of set B, but not for all elements in set B, okay? So for example, just the example now, like 1 is a proper subset of R, but you can't say that R is a proper subset of R, but R is actually a subset of R, okay? So the next one is the Cartesian product. So it's a set of all ordered pairs where A is in A and B is in B, as in the notation here. So one example is the 2D plane, like when you normally draw a single variable graph. So you have X and Y plane. So you can say that it's Cartesian product R times R. But you can also say that it's R squared in like some mathematical approach, like you write like this. Let me just write down. Like, if you have that, you can also write R squared. Okay, so the next ones are the intersection and union. So the first one is intersection. Is like kind of like an AND element. So set of elements that are both in A and B. So the next one is kind of like all elements or A or B, like it can be the set of all elements that are in A or B or both. So here, if we write or here, so it directly means that it's like not either A or B, but if one of A and B is true, then or is true. Like if we are meaning exclusive or, we'll write XOR. Yeah, like this. So we don't have notation for this. This means like A, the union of A and B minus the intersection of A and B, okay? So the next we're talking about logical notations. So the first one is like an inverted A, and it means for all X in A, okay? And the second one and third one means that there exists X in A. The second one is exists only one Y in B. Like if I write equals 1 is bottom right corner, it means there exists a unique y, or sometimes we can write some other things here. So for example, like there exists at most 2. You can write smaller than or equal to 2 here. So you can you're free to change something here to represent something different. So these are just some logical notations, or an AND. So just as I said just now, so or is inclusive. So the next ones are implies and if and only if. So implies just means if P is true, then Q is true. It's the same logical form as if you say if Q is false, then P is also false. But you can't say that otherwise. Like if Q is true, then P is true. It's not deduced this way. Like it's deduced in the if and only if. You can also write that as IFF. Like it's just okay. Let me just write down. It's also same as IFF if. So what this means is P is true if and only if Q is true. You can just say it in the other way. So it's still the same logical form. Q is true if and only if P is true. So if you try and prove that P is true if and only if Q is true, what you usually do is you prove that if P is true, then Q is true, and also prove that if Q is true, then P is true. Okay, this is like an AND statement, and both of them need to be correct. So, and the next symbol is like not. So statement is true if P is false, and vice versa. And the black square just means end of proof. Okay, so let's go to the definitions of functions. Okay, so we first let A and B be sets. Okay, so a function f from A to B, which is denoted this way, f colon and then A to B. So this satisfies the following conditions. So f is a subset of the Cartesian product A times B, and for all x in A, there exists one unique y in B such that xy is in F. So we'll probably use AB notation later, but just kind of let you guys familiar with like the proper like you're used to the graph system with like this way. So it's like xy here. So for example, you have the function like if I define function like this. So for all x in A, there exists just one y in B such that xy is in F. Okay, so this is, I just draw the graph of the function. I will define this later. Okay, so just as I say, let f from A to B and fx to x squared, and for example, let's let A equals B equals R. So we can just say that just here, just making clear, it's like you can write like this. This is the best way to write it. You don't need to define like A equals B equals R again. I just do this for a clarity. Okay, so for the first one, so f is a subset of A and B. So actually the Cartesian product A times B is equal to R squared. So f xy in R square, R y equals x squared. So this is just like the ordered pairs of f. Okay, so f is a subset of R square. Okay, so how to interpret it? Okay, so if we have R's for every x, so we have y that equals to x squared, which is a point in the y-axis of that graph. Okay, so it's also in R, but also the order matters, right? If you can't say like x equals y squared, so it's ordered pairs, and so it's a subset of R squared. So the first definition is correct. Okay, so for the next one, for each x in A, there exists only one and exactly one y that equals to that in B such that xy is in F. So this follows immediately from the construction. So we just say that y equals x squared, right? So this is unique and trivial, right? Okay. Okay, so let's go through some example. You may wonder, why is it a subset instead of proper subset? Okay, so probably I think most of the functions you have met is probably the elementary functions, so it's not piecewise function or some very like small domains. So so if I define it, so let A and B also equals to the subset just 1, and let fx equals 1, like that way. So then follows the immediate from construction that f is equal to A times B. Okay, so okay, we have some terminologies for the function. So first, the set A in the definition of f from A to B is called the domain of f. Let me write down. So to B. So this is the domain of f, A. So, and then B is the codomain of f, and it's different from range. Like codomain can be larger than the range. If it's equal to the range, we'll call it surjective, but I'll talk about this later in this next subsection. So for each x in A, the unique element B in B, such that xb is in F, is denoted by fx. So it's called the value of f at x, or the image of x under F. And the set of all images, fx in B, where x in A is called the range or image of F, where range F is a subset of B. Okay, so for example, we have just now the function fx equals x squared. So if we don't define the domain explicitly, we'll call it the natural domain is R. Okay, so it's from R to R, we can say. However, you should know that x squared with the x is a real number and not complex, so it's not possible to have fx as a negative number. So actually, the range of this function we'll say is the set of x in R such that x is larger than or equal to 0. Okay, so this is like a subset of R. So because there's a restriction on R, and it's like a part of R, so it can also be all of R. Like if I define the x cubed, so it can be not a proper subset but exactly equal to R. Okay, so first example, let fx equals to root x, so find the natural domain and range of f. Okay, so for f to be well defined, we need x to be larger than or equal to 0, because the square root function cannot accept an input of like negative number, otherwise it's out of the domain of the function if it's not defined to be complex. So we'll just, in this course, we'll just mainly discuss the functions in the real domain. So yeah, okay, so the domain of f is equal to every real number that is larger than or equal to 0, or we can just use this notation, which means it can be like this symbol means that it's attainable. And this symbol means that it's not attainable. So from the range from 0 to infinity, and it can be 0, but it can't be infinity. Like this is just definition thing. If we have something like not for this function, but if we have some notations like this, so if you consider 3 as valid domain of the function, so we'll use this. Otherwise, if 3 is not in the domain of this function, we'll use this, but we never use this symbol and this symbol for infinity. No infinity here. So the range is also equal, so it's all real numbers that are larger than 0, and then it's just the same. Okay, so let's go through some exercises. So are the functions below well defined? So for the first one, f from R to R, fx is the real number whose square is x. And for the second one, f from R to R, fx is smallest real number that's greater than x. Third one, f from Q to R, where Q means rational numbers to R real numbers. So f m over n equals m plus n. So, okay, so you may think a bit first. Also, you may pause the video if you need more time to think. Let me just switch the camera first. Okay. I hope it's clear. So are the functions below well defined? So actually the answer to all of them is no, they're not well defined. Okay, so for the first one, if we say fx the real number whose square is x, so what do we mean? So we can just give a context example that it doesn't comply with the definition with there exists only one y in the second in the range. So if we let x equals 4, then fx can be equal to 2 or -2. Then it's not the definition, so it's not correct, it's not well defined. So okay, for the second one, it has the same reason. So what do you mean by the smallest real number greater than x? It's not like a number that you can attain. If you say it's smaller, so you always have a smaller real number. So like if say x equals 0, so what does it mean? Like if we say fx equals 1 over 1000, it's not correct because 1 over 10,000 is smaller than it. Then you can just continue the sequence. So it's not correct in this way. So this is the definition part is not that it has multiple results, but actually the y doesn't exist. Okay, so there exists no y in B such that is in F. Like infinitely small, the concept of infinitely small isn't really like true number to be calculated in this way. Okay, so in the third one, we can just give a counter example again. So if we have m over n equals 1 over 2, this is equal to 2 over 4, right? So if we say here, if we plug in f 1 over 2, that equals 1 plus 2 equals 3, and then f2 over 4, you get 6, right? So but 1 over 2 is equal to 2 over 4, so we have 1 over 2 should be f1 over 2 should be equal to f2 over 4. So actually you have two values, or even more if you write like 3 over 6, and like it's not unique value. So if you plug in one number, you can have multiple results for that number. Okay, so let me go back to PowerPoint. Okay, let me just share it again because there's some technical errors in here. So okay. So okay, so we have the second exercise. Okay, so if we have fx equals the square root of x minus 3 over x minus 2, so find the natural domain and the range of f. So for you can have some time to think about it first. So I think the natural domain is pretty obvious. So, and then for the range, you may need some more thinking to get the range. Okay, so at the same time, let me just switch camera. Okay. Let me pause and think of it for some time. Okay, so let's begin. So for the natural domain of this function, you know that this function should be greater than 0, and then this one cannot be 0, right? So it's just x minus 3 is larger than or equal to 0, and x minus 2 is not 0. So this is x not equal to 2, and then x is larger than or equal to 3. So this is not actually an important condition, because whatever this number is, if you sub in 2, here won't be valid. 2 minus 3, like root of -1, is going to be I, and it's not in range. Okay, so we'll write the natural domain is equal to 3 to infinity. Okay, so for that range of f, so we have f x squared is equal to x minus 3 over x minus 2 squared. So we'll just replace this with y for simplicity afterwards. So fx, I just write it as y squared, then x minus 2 squared equals x minus 3. Okay, so y squared, x squared minus 2, 4x plus 4 is equal to x minus 3. So for that, we just get y squared x squared minus 4xy squared plus 4y squared equals x minus 3. So we would like to have a range of f. So that means we need to solve for an inequality in y. So what can you think of at this point? Okay, it's the quadratic equation. So we'll just rearrange it this way. It's 4y squared minus minus 1. So it's just like this, x and then plus 4y squared plus 3 equals 0. So for this equation, if you need x to have a solution, so it should be a real number, right? So 4y squared plus 1 squared minus 4y squared 4y squared plus 3, this is larger than 0. So by solving this, you need a quadratic equation. So after solving this, you get, I'm not doing the solving here, so I think it's just trivial. So you can just start from this equation, do it yourself. So yeah, and then this just b squared minus 4ac is larger than 0, this concept. Okay, so after that, you just get y equals 0 and 2. Okay, so actually you can, after solving this, this is larger than or equal to 0, sorry. So solving this, you have 0 to 1 over 2, which is inclusive of the range. Okay, so I'll just switch back to PowerPoint here. Okay, as I just say, the solution is like this. Okay, so let's go to the second definition, which is the graph of a function. Okay, so the graph of function from a to b is defined as the graph f equals the set of all ordered pairs a, b, in the set Cartesian product A times B, which B is equal to FA. It is just trivial, so just mean like, for example, if I just have an xy function, so if f from R to R, y, like if we say fx equal x, so it's like x fx, and then so it's xx. Yeah, so it's just trivial definitions. Okay, so we have the proposition 1.1.3, which is the vertical line test. So the set G as a subset of A and B, the Cartesian product of A and B is the graph of function f A to B if and only if for all A in A there exists a B in B such that A and B is in G. So this doesn't the first one doesn't require the uniqueness of B, so because we have to prove something later if we here use the uniqueness of B, so it's just like the definition of function directly. So if we are talking about graphs, so usually we'll not directly get like the uniqueness of B, so I'll just write in this way. So the second one actually is the uniqueness of B. Okay, so for all A in A, and for all B1, B2 in B, if we have A, B1, this pair is in G, and A and B2, this is also in G, so we can deduce that B1 equals B2. Okay, so let me just prove the forward direction first. Okay, so assume G, a subset of A and B, is a graph of a function f from A to B. So by definition 1.1.1, we have for all A in A, there's a unique B in B such that AB is in G. So we just write this as 3. So if we let A in A and B1, B2 in B, so if we suppose A and B1 is in G and A, B2 is in G, so this is just trivial, and this is true if we have A in A and like B1, B2 in G, we can make this assumption because so you can just make it a pair, so it's just like a construction of this. So by the uniqueness of B in 3, so B1 is equal to FA is equal to B2. So now we just prove that the first one, let me just, yeah. So we proved that the first one it exists, and the second one is unique, and B1 equals B2 is just the result. I just said, yeah. Okay, so for the backward direction, so we first assume 1 and 2 is true. So by 1, for all in A, there's a B in B such that AB is in G. So by 2, B is unique for each A. So this is just the assumptions we make just now. So it's just the conditions of the rightward direction. So okay, so if we define f from A to B by FA equals the unique B in B such that AB is in G. So G, which is the order paired AFA. Also, if we say AB is okay. So with A in A. So G is the graph of F. So it doesn't directly mean that there must be an algebraic expression for like a simple elementary function, arithmetic expression for that function, but this is a function that like is by definition exists, but it may not be good. So it can be something like f equals like we have piecewise function to define it this way. So x squared or x or 0 if x equals 0, if x is smaller than or equal to 0, more than 1, so we can just do something like this. Yeah, so this is like a piecewise function we'll define, but you meet more examples of piecewise function when we talk about like limits or continuity, that part. Yeah, so we have some application of the proposition homomorphy in the single variable calculus. So it's the vertical line test I just talked about just now. So if we have a graph like this, which is just f equals x squared, actually the graph. Okay, so all vertical lines intersect the graph at one and at most one point. Okay, so you can see here the intersection here, the intersection here. You can draw as all like first you know that like all the points here are just one. Like you can't find it somewhere in the other parts. So and then this one is x equals y squared, which is not graph of function if we're talking about fx. So if we draw a vertical line here, so you can see that it intersects at this point and this point. For every line, there's 2 points here. Like yeah, it's at this point. So we need that for all vertical lines, it intersects the graph at one and at most one point. Okay, so these are not correct. So this is not the graph of function. So this is the end of the first lecture of subsection 1.1. So thank you for viewing and goodbye.